as you know, field programmable gate arrays. So what is special about an FPGA? It's a field programmable gate array. So with that being said, it is a reconfigurable type of hardware. So me, I'm an electrical engineer, I'm focusing on hardware. So not quite as much as like, like you do comp sci stuff like software, like coding. I'm more focused on like hardware descriptive languages, actually creating different types of circuits that go into some of the designs that you have. And so with FPGAs, instead of like an ASIC, an application-specific integrated circuit, that's actually, the wires and everything typed into a certain like regular framework, FPGAs can be programmed and reprogrammed on the fly. So if you have a design, say if you have like an ADC and you have like a multiplexer or like a different type of multiplier, and it's already set in stone in the ASIC, the FPGA, you can change the design and change it around on the fly without actually having to go build an entire new circuit. So that's pretty cool with FPGAs. In my group, the Slammers group at Howard University, we focus on reconfigurable hardware FPGAs. They also have good advantages such as high processing power, so you can get really good clock speeds on them. So like if you're really using like a lot of accelerators, so if you want to make something really fast and just move faster, FPGAs are a good way to go. You might say, why would you use an FPGA versus like if you like play games like the GPU, like an NVIDIA or something like that, like the graphics ones that you have in like games. Those take up a lot of energy, but FPGAs are low power consumption. So if you're trying to do like real embedded like processing, like real embedded like designs, FPGA is the way to go because not only are you getting a high processing power, but you're also getting low power consumption. So now talking about SLAM, simultaneous localization and mapping. So ever since I got into engineering, I've been really interested in autonomous navigation, drones, self-driving cars, Tesla, like all of that stuff is really cool to me. So now when I came to Howard, I got under my advisor, Dr. Michaela Wu, and she introduced me to the idea of simultaneous localization and mapping, which is actually, let's just say like the framework for actually, one type of framework for actually doing autonomous navigation. So simultaneous localization and mapping is exactly what it sounds like. You have an unknown environment or area, and you want to map the area while also localizing where you're at the same time. So if I'm in this room right here, I want to say, where am I at in this room while also looking, seeing that I have all these chairs, these people in front of me, and also like these other obstacles around. So that if I wanted to path plan and go from point A, say from here to the door, I'll be able to have a direct line of where I need to go while also seeing my obstacles around me as well. So like I said, it's an algorithm for mapping an environment, definitely using context navigation. And then getting deeper into SLAM, you have visual SLAM. So, like if you're thinking about like Tesla, like you have the camera. So like visual SLAM is basically like camera dominant. So you have different types of visual SLAM, such as monocular, which is one camera, stereo vision, which is two cameras, which is basically like kind of how we like see with our eyes, like cameras. Like we use like with your eyes, like with glasses. And so there's different types of visual SLAM, and then going into SLAM, one of the most prevalent SLAM based algorithm is the oriented, fast, rotated, brief SLAM algorithm. And that's just a common fast feature detector and feature descriptor that's very used for our SLAM. And so just going into here, I just wanted to show you, this is a very big block diagram of both the ORB SLAM and ORB SLAM 2. The difference between the two is one is just straight monocular, and as you see, the one on the right has a lot more added parts because it takes in binocular vision, while also stereo vision, and also even RGB depth cameras. So the one on the right is just more complex because it allows for different types of inputs from different camera images. But the main thing with showing this algorithm is not to really focus on that part, but as you see all these most important parts, I don't know if you can see my mouse, but when you get into like trying to make things faster, put things on embedded devices, and trying to put it in real world applications, you want to accelerate the most time-consuming computational part of the algorithm, which happens to be the local bundle adjustment. Actually, the bundle adjustment, but the local bundle adjustment is kind of like by the local mapping, and then on the other side is one over by the full BA. But that takes the most time complexing part for actually putting this algorithm on like an actual embedded device. So as a hardware engineer, when looking at how to make something faster, we're looking at how do we improve the bottleneck. So before I get into how do I improve the bundle adjustment bottleneck, I had to learn what bundle adjustment was. And so bundle adjustment is a nonlinear least squares optimization problem, where the objective is to find the 3D points and camera parameters that minimize the reprojection error. So the reprojection error is going to be the error in like layman's terms between the point that I see and the point that I predict, and we're putting that back into 3D points. So I have this diagram over here. So like the camera cameras are the little C's at the bottom. I got this from the paper that I was really diving deep into. And so the cameras, you have cameras takes the pictures of the images, and the pictures of the images are then raised to frames. And then from the frames, you could take the image that you have from, like, say, like that 3D dimensional shape that you see has different images from like a different size. So now you have those points, and so then you have the observations and the actual point, and then you want to get to actually the 3D coordinates of it. But you want to minimize the area of like your actual predictions as much as possible so you can have an accurate representation of the map. And so this is like the most important part, but it's also, like I said, the most time consuming part. So there's been a lot of different ways to like attack window adjustment within research, but from what I've done in my literature survey, I've seen that a lot of the ways have been attacking the actual algorithm that minimizes the reproduction here. The 11 bar Marquardt algorithm. The 11 bar Marquardt algorithm is a very old algorithm. It's a standard algorithm to solve the bundle adjustment problem. It's just an iterative technique to really just kind of iteratively go down and minimize whatever type of function that you use. So it's not specific to bundle adjustment, but it's using bundle adjustment really just so that you can minimize any type of like L2 norm error. And so within the 11 bar Marquardt, you have 5 different parts. It's math heavy, so you have the Jacobian updates. So because we have all these camera parameters, it fits well for this problem because these camera parameters, such as like having different points, they get put into these different matrices. So then they get put into these big matrices that have to be split up and operated around. And so the Jacobian is you're gonna have to be using a lot of differential between the differential of the different partial differential of the different components. So that's one part of it. And then you got the square elimination. So when you're trying to solve for the most efficient part of it, so then you can create like the S matrix to get to the step variable to move faster with another algorithm. And so that is one part of it too. And then you have Jacobian factorization, then the cost function computation, and then the gain ratio evaluation. So going from there, splitting up the 11 bar Marquardt in 5 different algorithms, 5 different spots. Now looking in that aspect and seeing which one takes the most time complexity, actually is the square elimination. So here's information from one paper where they actually put bundle adjustment in hardware, and then they also said, okay, the 11 bar Marquardt is how we're going to be able to accelerate bundle adjustment. Now let's do a code software hardware design, so where you put the items in the left are put in the software, and then the items in the right are put designed to hardware. And then the next block to the right over there is basically just a block diagram of how they would do the square elimination basically in hardware. So instead of doing like a software algorithm, it just broke down all the matrix calculations and everything into simple terms of adders, multipliers, and then like different hardware components such as like RAM and just like RAM. And so that's how we do things in hardware, so we're able to break things down to simple components of that. So moving forward, just real quickly. So with that information, that's pretty cool, but a lot of that work has been done kind of like in the old, I won't say the old, but like I want to kind of throw a new spin on it too as well. So now, how do we add some new stuff on top of like other stuff that I've talked about before? So that's where graph neural networks comes in. So when you have these 3D points and these 3D projections, they can be represented in a graph-like structure. So with that, you could actually take out the 11 bar Marquardt algorithm and actually create a graph-like neural network to where you can train on the inputs of the graph and then actually get back the optimal observations afterwards. So like I said before, you just have the input being camera poses and landmarks, and then the output will be the optimized values. And then this graph neural network, you were replacing the 11 bar Marquardt algorithm, but you would actually just inspire the graph neural network would be from that as well. So this is just a diagram of like from one of the papers that actually did this, where they had an initial values before, like I said before, and then they put it through a graph neural network block. So just closing it real quick. So with my research is where I'm at the end of the literature review stage, and now I'm diving into how I'm going to move forward. So I'm putting all these things together, the hardware acceleration of FPGA, SLAM algorithm, the graph neural network based bundle adjustment, and there's different parts we go into it. Math, which understand the matrix operations, and then software side, so I'm actually creating these bundle adjustment algorithms, which are mostly in software and the graph neural network, and then taking the hardware and converting it to software, from software to a hardware descriptive language, using a high-level synthesis tool. If you want, please ask me a question about it, and And then our specialty within our lab, which is FPGA implementation. So we have all these complex hardware designs, now let's put them on FPGA so that we can prototype it out and actually put it into work into the real world. That is the end of my presentation. Questions, comments, suggestions?
Literature review, what have you found to be, I guess, the gaps in the literature? Like, is there anything that you're finding a particular gap in each of these parts that you mentioned? I can't even say all of the different ones, but.
Yeah, so like, even like putting this presentation together, I had to like cut out a lot just to get it 10 minutes, but I've seen a lot of papers that really started off where like, instead of like just going deep into like creating a hardware specific like accelerator, they would do like parallel processing. So they're putting like different parts and like running them together at the same time. Or they're just like, we're gonna just get some heavy artillery like GPU, like a big computational device and just make it real fast. Or they'll do like a software computation where they like change certain things and just try to make it faster. But those don't really materialize into like actual real world applications, because when you go from, okay, we can do this real cool and just like a theoretical, like, or like a simulation, but if you want an autonomous car, you have to make sure that it's not only able to drive us on and sense things around, but also be able to keep up with the power restrictions, like talk to the other parts of the car as well, and read those types of, because it's not just about the computing aspect, like you have the wheels, you have like the axles, like all that stuff has to be in sync to them. So in the literature, I just seen like a lot of people just throwing like big like hardware and stuff and just doing computation without actually thinking about the other parts that go along to these applications. So when I really like broke it down, I made sure that I was like, okay, what is going to be useful for me to make something that actually is prototypable and useful? So I focused on that when I was seeing the literature. Does that answer your question?
Yes.
First, pretty good presentation. I like the area where you're focusing it on. When you say navigation, autonomous navigation, I know a lot of the major companies are focusing on like urban areas to an extent. You know, like I guess with roads or buildings, and kind of understand their environment that way. But what about for rural areas? Would you say your work will be able to autonomously navigate in rural areas as well, to where there are more like not as many buildings, maybe the roads aren't as constructed, as like may not have like lane markings. And so do you see this being applicable to rural areas as well?
Yeah, I gotta give props to my advisor, Dr. Michaela Moon, because I walked in as a graduate student, like, why am I doing SLAM? What is the purpose of this? But like SLAM actually is for that exact reasoning right there, for when you have an unknown environment, even going deeper into unknown terrain. So like it works for indoor environments, like say if like you have a room like this, or if you're out in a unknown terrain, say if you are in a rural area, just even if it's not even just a rural area, say if it's dark outside, say if you don't have much light, like SLAM works for any type of unknown environment. And that's just in the straight literature, just how like it's been used for like those two cases. But this algorithm is particularly for that when you really don't know your outside conditions.
Okay, sure. Just for that, I'm not sure if you're gonna leave with this.
Oh, no.
I have a question.
Okay.
Yeah, it was a great presentation. So I was wondering, you mentioned that PGAs are like more robust than GPUs for hardware acceleration when you're algorithms like the LM. Is it still true when you scale up to GNNs or larger neural network operations?
Didn't want to say that they're more robust, just in the sense that they have similar high processing power and speeds, but for less power consumption. That's just really what I'm like. But I haven't gotten so far into the studying the GNN part. That's the next part that I'm going deeper into. But I will look into that and see how they measure up with that specific type of GNNs when it comes to a GPU or FPGA. But from what I've seen right now, the FPGA, especially when it comes to like bundle adjustment and that aspect, very favorable in processing power at like the same time, you can reiterate that, but just really the benefit comes in the lower power consumption. Yeah. Did I answer your question?
Yeah, thanks.
Anything else? Well, got my references here. Thank you for your time today.